Hi friends, welcome to the YouTube channel Civil Vision Tune Yourself. This platform is specially for civil aspirants who are preparing for competitive exams. There are many channels and websites available these days for providing materials, classes, online test series. In our channel, we will be providing a platform to enhance knowledge-oriented classes. Most of the competitive aspirants are well versed in learning concepts, but they lack application of this. This is great debacle for the aspirants who are appearing the exams directly. Kindly join with us and use this chance for improving your preparation. Most of the people face difficulties in concepts and analytical oriented problems. We request you people to join with us and brush up your analytical knowledge for just 15 minutes per day. We guaranteed for that 15 minutes. We usually upload 10 minutes video for technical and remaining 5 minutes we generally discuss about general facts. If you like this video, kindly share with your friends who are preparing for competitive exam. Thank you so much for your patience. These are the topics which we are going to cover in upcoming classes. First one, strength of materials. Why I choose strength of material as the first one? Because it is the basement for most of the subjects in civil engineering. Strength of materials. This is the syllabus of strength of materials for TNPSC and board exams. Based on our convenience, we split the syllabus into 5 parts. First one up to elastic constant, second one up to shear force in beam, third one up to buckling of column, fourth one up to principal planes. Rest of this are part 5. Part 1. Simple stress and strains, thermal stress and elastic constants. Stress. It is defined as the resistance offered by the body to deformation. Nominal stress or simple stress equal to load by original area or resistance by original area. Actual stress or true stress equal to load by changed area. Stress is a derived quantity, therefore unit of stress is Newton per mm square. Strain. It is defined as the deformation per unit length in the direction of deformation. Strain equal to change in length by original length. Strain is the fundamental quantity, therefore no unit for strain. Stress strain curve of mild steel for tension under static loading condition. The graph is drawn between stress in y direction and strain in x direction. The portion between O and P is a proportionality limit. The stress at which stress strain curve ceases to be a straight line. In this limit, stress is directly proportional to strain. Hooke's law is valid up to this limit. The portion between O to E is called elastic zone. In this zone, there is no permanent deformation after removal of load. And it is also called as a stress strain curve which materials remains elastic. Y1 and Y2 is the upper yield point and lower yield point. Y2 is considered as the yield point of mild steel because it influences less amount in shape than compared to upper yield point. After the lower yield point, the stress reaches the ultimate point due to strain hardening. The ultimate tensile stress of the mild steel is 410 MPa. After the ultimate point, graph starts fall and reaches the failure point. Failure point is also called as a rupture strength. It is the stress corresponding to the failure point of the stress strain curve. This is the apparent graph of mild steel. The portion between E to U is called plastic zone and U to F is called necking zone. Type of tension failure. Ductile material. It is defined as the post-elastic strain is greater than 5%. It undergoes large permanent strain before failure. Large reduction in area before fracture. Example of ductile material is lead, mild steel, copper, etc. A bar subjected to a tensile load P, there is a Fracture like cup and cone fracture in ductile material, and failure plane is 45 degree. Brittle material. Brittle material is defined as the post-elastic strain is less than 5%. It fails with only little elongation after the proportionality limit is exceeded. Very less reduction in area before fracture. Example of brittle material is bronze, rubber and glass. Brittle material subjected to a tensile load P, the failure plane at 90 degree with longitudinal direction. Necking is not formed in brittle material, but in ductile material necking is formed. Type of compression failure. In ductile material, the failure is like buckling. In brittle material, shear failure takes place at 45 degree. Hooke's law. Hooke's law is defined as stress is directly proportional to strain up to proportionality limit. To remove the proportionality by introducing a proportionality constant E. Therefore, stress equal to Young's modulus into strain. Axial elongation of prismatic bar due to external load. Let us consider a bar subjected to a tensile load P. That is elongation or deflection equal to PL by AE. AE is the axial rigidity of that material. Deflection of the bar due to self weight. Prismatic bar deflection equal to gamma L square divided by 2E. In conical bar, deflection equal to 1/3 of the prismatic bar. Therefore, gamma L square divided by 6E. Elongation of non-prismatic bar. There are two types of non-prismatic bar. First one is stepped bar, another one is tapered bar. In stepped bar, elongation equal to PL by AE. In tapered bar, for circular section, deflection equal to 4PL divided by pi D1 D2E. D1 is the larger diameter and D2 is the smaller diameter of the bar. For rectangular section, deflection equal to PL by ET into capital B minus small b log base of capital B divided by small b. Elastic constants. Elastic constants are those factors which determine the deformation produced by a given stress system acting on the material. There are two isotropic elastic constants. They are Young's modulus and Poisson's ratio. Young's modulus is defined as stress by strain. Poisson's ratio is defined as lateral strain to the longitudinal strain under uniaxial loading. Relation between bulk modulus and Young's modulus. Bulk modulus is defined as direct stress to the volumetric strain. Therefore, E equal to 3K into 1 minus 2 mu. When K equal to E, Poisson's ratio equal to 1 by 3. Relation between modulus of rigidity and Young's modulus. Modulus of rigidity is defined as shear stress to the shear strain. E equal to 2C into 1 plus mu. When bulk modulus equal to modulus of rigidity, Poisson's ratio equal to 1 by 8. Mu equal to 3K minus 2C divided by 6K plus 2C. This is the relation between Poisson's ratio, modulus of rigidity and bulk modulus. Therefore, Young's modulus equal to 9Kz divided by 3K plus C. These four formulas are very important in elastic constant. We expect one question in elastic constant. For orthotropic material, there are 9 elastic constant. For anisotropic material, there are 21 elastic constant. Thermal stress and strain. Thermal stress is a stress created by any change in temperature to the material. Thermal stress is caused due to temperature gradient, thermal expansion or contraction. Case 1. No restriction for expansion and contraction. Therefore, strain equal to alpha del T. Change in length equal to L alpha T. When a bar is free to expand, then there will be no thermal stress due to change in temperature. Case 2. Restriction for expansion and contraction. Thermal stress equal to alpha TE. Therefore, the thermal stress exists. These are the sum of the materials and their thermal coefficient. Now we are going to solve the analytical problems which is related to above topics and which is repeatedly asked in competitive exam. First question, a steel rod 100 mm long is held between free support. It is heated by 20 degrees Celsius. Thermal coefficient of the material is 15 into 10 power minus 6 per degree Celsius. Modulus of elasticity is 200 into 10 power 3 meganewton per meter square. What is the stress in the rod? Stress is nothing but thermal stress. First find out the keyword in the question. Keyword is free support. We already know when a bar is free to expand, then there will be no thermal stress due to change in temperature. Therefore, the thermal stress in the rod is 0 meganewton per meter square. Suppose it is held between fixed support, there will be thermal stress exist. Thermal stress equal to alpha TE. 20 into 15 into 10 power minus 6 into 200 into 10 power 3. Finally, the answer is 60 meganewton per meter square for fixed support. A rod which is held between free support 0 meganewton per meter square, which is held between fixed support 60 meganewton per meter square. Next question. Second question, if the modulus of elasticity for a given material is twice its modulus of rigidity, then bulk modulus is equal to. We very well know about elastic constants. Now write the relation between modulus of elasticity and bulk modulus. Equal to 3k into 1 minus 2 mu. Given equal to 2c, substitute the value, find out the bulk modulus k equal to 2c by 3. We expect one question in this area. Next question. Same model question. Lead as a material used in construction has Young's modulus 15 GPa, bulk modulus 50 GPa. What is the Poisson's ratio? We know the relation between Young's modulus, bulk modulus and Poisson's ratio. The same formula which we used previous, equal to 3k into 1 minus 2 mu. Substitute the value, equal to 15 into 10 power 3 Newton per mm square. 3 into 50 into 10 power 3 Newton per mm square into 1 minus 2 mu. Find out the Poisson's ratio. Poisson's ratio for lead is 0.45. Next question. A pull of 20 ton is suddenly applied to a rod of a cross-sectional area 40 cm square. The stress in the rod is equal to. We already know about the formula for stress. Stress is nothing but load by area. The keyword in the question is suddenly applied load. For suddenly applied load, stress is nothing but 2 times the applied stress, 2 times the load by area. Therefore, 2 into 20 ton divided by 40 cm square. Therefore, stress in the rod is 1 ton per centimeter square. Next question. A load of 1 kilonewton acts on the bar having a cross-sectional area 0.8 cm and length 10 cm. Stress developed in the bar. Stress is nothing but load by area. Load equal to 1 kilonewton. Area in the bar is 0.8 cm square. Find out the stress in Newton per centimeter square. Convert the unit into Newton per mm square. 1 centimeter equal to 10 mm. 1 centimeter square equal to 100 mm square. Therefore, substitute the unit conversion. Find out the answer for stress equal to 12.5 Newton per mm square. Next question. A steel bar of 100 mm long subjected to tensile stress. If the change in length of the bar is 1 by 20 mm, and what is the value of the stress? We already know the formula for stress. Stress is nothing but load by area. But here the change in length is given. Therefore, use the formula. Stress is directly proportional to strain. This is what Hooke's law. Stress equal to Young's modulus into strain. Strain equal to change in length by original length. Change in length is 1 by 20 mm. Original length is 100 mm. Therefore, Young's modulus is 1 by 2000. Substitute the value. Stress equal to 1 by 2000 into Young's modulus equal to 2 into 10 power 5. We already know the Young's modulus for steel, 2 into 10 power 5. The first stress in the rod is 100 Newton per mm square. Next question. The length of the wire is increased by 1 mm on the application of certain load. If the wire of the same material but twice the length and half the radius, therefore same force will produce elongation. We know the formula for elongation, delta equal to PL by AE. Length get twice and radius reduced by half. Therefore, area formula, which is equal to pi r square. R equal to 1 by 2. 1 by 2 the whole square, which is equal to 1 by 4. 2 divided by 1 by 4. Therefore, the elongation delta equal to 8 times the PL by AE. Therefore, the elongation produced is 8 mm. Next question. A cylindrical bar of 20 mm diameter and 1 meter length is subjected to a tensile test. Its longitudinal strain is 4 times its lateral strain. The modulus of elasticity is 2 into 10 power 5 Newton per mm square. Find the modulus of rigidity. We know the elastic constant for a relation between Young's modulus and modulus of rigidity equal to 2c into 1 plus mu. Poisson's ratio is nothing but lateral strain to the longitudinal strain. Therefore, 1 by 4 equal to 2 into 10 power 5. C have to find the modulus of rigidity. Therefore, substitute the values and finally find out the modulus of rigidity equal to 0.8 into 10 power 5 Newton per mm square. Next question. A copper bar of 25 cm length is fixed by a support at its end. Supports can yield by 0.101 cm. If the temperature of the bar is raised by 100 degrees Celsius, thermal coefficient is 15 into 10 power minus 6 degrees Celsius. Young's modulus is 1 into 10 power 6 kilogram per centimeter square. Stress induced in the bar. Stress is nothing but thermal stress. We already know the formula. Thermal stress equal to alpha TE. But here the support can yield 0.0 centimeter. Therefore, alter the formula as the thermal expansion is prevented formula. Therefore, E by L into L alpha del T minus delta L. Substitute the values for Young's modulus, length and change in length, thermal coefficient. Finally, find out the answer as 1600 kg per centimeter square. Therefore, stress in the thermal stress produced in the rod is 16 into 10 power 2 kilogram per centimeter square. Remaining problems will discuss tomorrow. Now we are going to see the general facts about World Heritage Sites. First one, Ellora Caves. On 1983 onwards, it is considered as a World Heritage Site. It is located at Aurangabad district, Maharashtra. There are 34 viharas and temples are there. 34 viharas are broadly classified into Buddhism, Jainism and Hinduism. In Buddhism, there are 17 viharas. In Hinduism, 12 viharas. And in Jainism, there are 5 viharas are there. Period of construction of Ellora caves is 600 Common Era to 1000 Common Era. Most remarkable cave temple of Ellora cave is Kailashanada temple, and it is named as 16th cave temple, which is also called as the largest rock cut monument in the world. It is built by Krishna I of the Rashtrakuta dynasty. Period of construction is 8th to 9th century. This is the minimal information about Ellora caves, and it is enough for RRB and SSC exam. Thank you.